The final thing we're going to talk about here with circuits is looking at situations where we have a bunch of resistors connected, but they're not connected in a simple series or simple parallel circuit. It's going to be some combination of series and parallel. Okay, so something like this circuit here. Okay, we see these two are in series, but the whole circuit is not a series. We see this is in parallel with these two, but the whole circuit's not a parallel. So we're going to look at first how we get the resistance of a circuit like this, and then we'll do a full analysis like we've done before for basic series and parallel. So the key thing here is we're going to look for simple combinations. We're going to look for 2 or maybe 3 resistors that are in a simple series. And in this case, that would be these 2 resistors here. Okay, and then we're going to combine those resistors using our rules, right? So for series, we just add them up. For parallel, we do that 1 over equation. Okay, so we'll combine them, and then we'll redraw the circuit. So we've now replaced these 2 resistors with this single resistor here. And then we find the next combination. So these 2 in parallel, and we combine those and redraw the circuit. So those 2 become this single resistor here, and then we find the next combination, and so on. The easiest way to learn how to do this is to work through an example. So let's do that. So here we have a circuit that we're going to go ahead and condense and find the total resistance of, and we're going to start by looking for examples of simple series or simple parallel circuits within this more complicated circuit. And so the first thing I see here is we have 2 resistors in parallel, R1 and R2, and so I'm going to find the total resistance of that. So it's going to be 1 over RT equals 1 over 10 plus 1 over 10, and when we go ahead and solve for that resistance, it's going to be equal to 5 ohms. And I'm going to call that resistance R12, the combination of 1 and 2. We can look for another simple combination, like what we have here. So 3 and 4, so 1 over RT is equal to 1 over 18 plus 1 over 6. And when we combine those 2 resistors, we end up getting a total resistance here of 4.5 ohms, so that's going to be R45. We also can combine these 2 in series, 6 and 7, and so for that we're just going to add them. So it's just going to be 5 ohms plus 4 ohms, and so R67 is equal to 9 ohms. All right, and lastly we have resistors 8 and 9 here. Once again, another simple series combination, so we're just going to add those 2, 2.5 and 3.5, and so we get a total resistance here of 6 ohms for R89. Now that we've found all of our simple combinations, what we're going to do is redraw the circuit, although you have below that circuit already redrawn for you, and we're just going to fill it in with these equivalent resistances or total resistances that we got from combining those simple combinations. So we have here our new circuit that we've replaced those combinations of resistors with a single resistor, right? 1 and 2 were both 10 ohms. They combine in parallel to form a 5 ohm resistor. And then same thing for 4, 5, 6, 7, and 8, 9. So we're going to look for another simple combination that we can combine, and what I see right here is these 3 are all in parallel, so we can combine those. So 1 over RT is going to be 1 over 4.5 plus 1 over 9 plus 1 over 6. And when we solve for that, we end up getting 2 ohms, and so that's going to be R4, 5, 6, 7, 8, 9. The equivalent of those 6 resistors all combined to be a single resistor with 2 ohms. And now we're going to redraw the circuit and look for our next simple combination. So I had my 5 ohm resistor from before, R12. I now have my new resistor, 4, 5, 6, 7, 8, 9, all combined to be a 2 ohm resistor. And now it's just a simple series circuit. And so I can just add up that series, 5 plus 7 plus 2, and I get a total resistance here of 14 ohms. And so all of those resistors combined, that combination of series and parallel, all of those resistors end up being the equivalent of a single 14 ohm resistor. Okay, that's the total resistance of our circuit when we reduce and condense all those resistors to a single resistor. All right, so we're now going to put all of this together. Okay, and what I mean by that is we're going to take a look at a complex circuit, and we're going to find the total current through the circuit, the total resistance of the circuit, and then the voltage and current through each one. Okay, and so a few tips here. We're going to start by breaking down the circuit as a whole, finding the overall resistance, redrawing it each time. I know it seems like a little bit of a pain, and it might be tedious at times, but it's not a difficult process, and it makes it a lot easier if you break it down and redraw each time. Okay. Once we've reduced it to a single resistance, found the total resistance, we're going to solve for the overall current. From there, we're going to start putting the circuit back together again, working backwards, using our voltage and current rules, using Ohm's law. Okay, if we know the resistance of one of our resistors and we know either the current or the voltage, we can use Ohm's law to solve for the other one. And we'll keep working backwards until we've built that circuit back up and we know the resistance and current on each individual resistor. Once again, it's probably easiest to look at an example of this, so let's go ahead and do one. Alright, so let's start by working through this example problem here. So we're going to start by breaking this down into a single resistor, and we're going to look for combinations of resistors. So the first one I see here is 5 and 6. Those two end up combining to be a single resistor, R5, 6. And we're going to, I'm just going to do the math rather than writing it out each time to save some space here. But we are doing that 1 over trick, and they end up combining to be 6 ohms. Okay, we're combining them in parallel. The other combination I see here is 2 and 3. They are connected in series, and so we're just going to add those two, and we get a total resistance there of 35 ohms for 2 and 3. So I've now gone ahead and redrawn my circuit here. We can see that I've replaced 5 and 6 with this single resistor here of 6 ohms. I replaced 2 and 3 with this single resistor here of 35 ohms. Now I'm going to look for my next combination and combine them. So I see that these two are connected in parallel, 2, 3, and resistor 4. And so I'm going to go ahead and combine those to get the total resistance of them in parallel using the 1 over equation here. And so we end up getting a resistance of 10 ohms for those 3 resistors ultimately that are combined. Now we're going to go ahead and redraw our circuit once again. So I have my circuit redrawn here. Now it's just a simple series circuit. All of these can be combined to get a total resistance here, and that's just going to come from adding them all up, and we end up getting a total resistance here of 20 ohms, 6 plus 10 plus 4. And so that's the resistance of all 6 of those resistors combined. Now that I have that, I can solve for my total current, the current that actually leaves the battery, using Ohm's law. So we have 30 volts total being supplied by the battery, a total resistance here of 20 ohms, and so my current that ends up leaving the battery is 1.5 amps. All right. Now that I have this part here, okay, now that I have my total current and my total voltage, what I can do is I can start working backwards and filling in the current and voltage for each one. So we're going to start with that, and you want to use your voltage and current rules, and you're going to want to use Ohm's law. So I'm going to start with the currents here. I know these are all connected in series, and so this 1.5 amps is going to flow through all of these resistors. So that means that this one gets 1.5 amps, this one gets 1.5 amps, and this one gets 1.5 amps. I can then use Ohm's law to solve for the voltages. All right, so V equals IR, that's what we're going to be doing every single time. That's going to be a huge equation as we're going through and solving this, but I'm not going to write out each individual one because that just gets cumbersome. But using Ohm's law, we can do 1.5 times 4 ohms. We get that this one has a voltage of 6 volts, 1.5 times 10, this has a voltage of 15 volts, and 1.5 times 6, this one has a voltage of 9 volts. We see that they do add up to our total voltage of 30. Okay. Now that I have that, I'm going to step this back one. Okay, so I'm going to go to my middle drawing here, and I'm going to fill in what I got from the last one. So I know that R1 is 1.5 amps, and it's a voltage of 6 volts. That hasn't changed. R5, 6 is still there, and so that's going to be 1.5 amps. And a voltage here of 9 volts, all right? But these resistors were not present in my last one. These guys combined to be a single resistor here. So we got to step this back one, okay? We got to take these resistors and separate them back out. So they were connected in parallel. That's important, Okay, and you could use your voltage rules to determine that this one must be 15 volts and this one must be 15 volts if we think about our loops. Or you can just keep in mind that resistors in parallel get the same voltage. So when we separate this one, okay, into two parallel resistors, each one of those resistors will get a voltage here of 15 volts. Okay, and now that we know that, we can go ahead and solve for our current through each of those resistors. So when we use Ohm's law here to solve for that current, we end up finding that the current through R23 is going to be 0.43 amps. Okay, and the current through R4 is going to be 1.07 amps. Those are rounded slightly, but those are going to be the currents, and again, that's just using Ohm's law. All right, we're going to then step this back one more, back to our original circuit. And so there's a few we can fill in right off the bat. We know that R1, that was an original resistor, has 1.5 amps, and that has 6 volts. Okay, didn't come from any combination. We know R4 has 15 volts, and it has a current here of 1.07 amps. And then we can go ahead and solve for the voltage and current for these two and the voltage and current for these two. So let's start with 5 and 6. All right, they were connected in parallel. They ultimately led to this 6 ohm resistor, which had 9 volts and 1.5 amps. That means that each one of these resistors will get 9 volts. And we can go ahead then and solve for our current. So the 24 ohm one is going to get 0.375 amps of current through it. And the 6 ohm one is going to get 1.125 amps of current running through that. Last thing to do here is to find 2 and 3. They came from this resistor, R23, which had 35 ohms. Since they're connected in series, they don't both get 15 volts. They do, though, both get 0.43 amps. Right? That current through them is going to be the same. So they each get 0.43 amps of current here. And then we can use Ohm's law to go ahead and solve for the voltages. So the 20 ohm one is going to have 8.6 volts on it. The 15 ohm one, R3, is going to have 6.5 volts across it. I realize that doesn't perfectly add up to our 15 volts here. It actually adds up to 15.1, but that just results from rounding. If we hadn't rounded at all, we would have gotten an exact answer that added up to 15. So there's your final circuit. It is a little bit messy, but the idea, we can see we're first breaking down this circuit, so we're working our way down to get to a total resistance here, all right? And then we're going to slowly build it back up, all right, solving for the voltages and currents for each individual resistor until we get back to our original. So we have another practice problem here. We're going to start by looking for our simple combination of resistors. So I'll start with 2 and 3 connected in series, and so that total resistance, R23, is going to be 12 ohms, just adding them up. And then we have 4 and 5 are connected in a basic parallel circuit. And so when we combine them, we get a total resistance there of 3 ohms. Now I'm going to go ahead and redraw our circuit. We now have our circuit redrawn here, and so we'll look for another simple combination, and we see we have those two in series. So that means that R456 is going to be equal to 4 ohms. We're going to go ahead then and redraw our circuit another time, replacing that with the 4 ohm resistor. So here's our redrawn circuit, and we once again find the simple combination, and it's these two in parallel. We have to be a little bit careful. It might be tempting to say this one's in parallel too. However, you have to consider this is the point where the circuit splits. This is where it comes back together. That R1, even though this line is parallel to those two, is not in parallel with these two. In parallel means the circuit splits. You go one way or the other, and then the circuit comes back together. So when we combine those two resistors there in parallel, we end up getting the total resistance here for R2, 3, 4, 5, 6, and that ends up being 3 ohms. All right, and then we're going to redraw our circuit one last time and be able to finish this. So for our final step here, we just have two in series with each other, so the total resistance of all 6 of those resistors combined is just 3 plus 3, or 6 ohms. Now we know that the current running from the battery here, it's listed as 4.5 amps. So now we can start working backwards and finding the voltage and current for each one. Since this is a basic series, that means that each one of these resistors gets 4.5 amps of current. We can then solve for the voltage across each one. So 4.5 times 3 using Ohm's law here is 13.5 volts. And 4.5 times 3 as well here also gives us 13.5 volts. So keep in mind, we're going to be using Ohm's law a lot as we work backwards and find the voltage and current on each individual one. Now that we have that, we'll step it back one more. So stepping this back one, we see that R1 here is the same as R1 here, 4.5 amps and 13.5 volts. We can now take a look at R23 and R456, which were combined as a single resistor in the previous circuit. And so since they were in parallel, it means that each one will get that full voltage. So each one of these will get 13.5 volts across it. And then we can solve for the current running through each one. So the current for the 12 ohm one using Ohm's law is going to be 1.125 amps. And the current for the 4 ohm one using Ohm's law is 3.375 amps. We can now step this back one more. So we can go ahead and step this back one more. We're going to take this R456 and separate it into R45 and R6. So they were connected in series, which means that each one is going to get that full current here. So that means that each one gets a current of 3.375 amps. And then we can use Ohm's law to solve for the voltage across each. So the voltage across this one is going to be 3.375 volts. Voltage across this one is going to be 10.125 volts. Now we can step it back one final time to get back to our original circuit. So I went in and filled in the ones that don't change. So that would be this R1 and this R6. They're the same as they were in this circuit. What we need to do now is expand out this R45. Those two were connected in parallel, so they each get the same voltage. So this R4 is going to be 10.125 volts, okay, and R5 is going to be 10.125 volts as well. And then we can solve for the current on each one. So the current through R4 using Ohm's law is going to end up being 2.53 amps, and the current that we get using Ohm's law once again for R5 is going to be 0.84 amps. The other one that we need to separate out is this R23. We need to split it into R2 and R3. They were connected in series, so each one gets that full current, so each one's going to get 1.125 amps. And then we can go ahead and solve for the voltage across each one using Ohm's law. So this one ends up being 2.25 volts, and this one ends up being 11.25 volts.